All right, welcome to kind of our last introductory topic here in chapter 4. That's going to cover redox reactions. It's kind of the last really major reaction type, at least as far as kind of aqueous reactions that we see here in 1211 that we're going to talk about right now. And this type of reaction involves things that are a little bit different. A lot of our reactions previously can almost describe as like a double displacement reaction in terms of being able to exchange ion pairs to be able to predict products from the reactants that you start with. Redox reactions are a little bit more complicated, and really even throughout 1211, you're never really going to be able to, or at least expected to, predict products for a redox reaction. There are examples like combustion reactions, for example, are a oxidation reduction reaction, or sometimes called a redox for short. And you can probably predict the products on those reactions specifically, but not just generically all oxidation reduction reactions. Maybe once you get towards the very end of 1212 and kind of come back to some things with electrochemistry and talk about reduction potentials and see reactions involving reduction potentials, then you can start to make some better predictions as far as products. But for the most part, redox reactions, you'll probably be given the full reaction all the time. And so it's much less about knowing what the products are going to be and much more about understanding what's actually changing during the reaction. Because the biggest thing with redox reactions in general that's very different from everything that we've kind of seen so far is that redox reactions involve the exchange of electrons from one element to another. So we are basically, taking electrons and kind of moving them between different atoms in this reaction, whereas a lot of other types of chemical reactions, it's just how the electrons are kind of bonding between atoms, but then each atom kind of can take its own kind of electrons back in terms of breaking and forming new bonds. So it's a little bit different here. We actually have the full-on transfer of electrons during our process, and it results in the change of something called the oxidation states for those elements that either gain or lose the electron. Now, in terms of kind of some of the terminology involving oxidation reduction reactions, the term oxidation really just means that something is losing electrons. This does mean it's going to get more positively charged as a result, since our electron's a negative particle. And this always then gets paired with reduction, which is the gaining of electrons by something, which results in kind of a more negative charge instead. And then there's a couple different mnemonic devices that people will try and use to kind of keep these terms straight, because you do want to know what each one is. And kind of the first of which is oil rig. This is probably the oldest one, where again, oxidation is loss, reduction is gain, and just kind of as far as the acronym there. And then you'll have probably the more recent one I've known a lot of students have used is Leo the lion goes grr. Leo being the losing electrons is oxidation, gaining electrons being reduction, then for the second part of that. And again, they're just kind of helpful mnemonics to try and help you kind of keep the two straight. Because you will be asked, some of the questions you'll be asked to identify is when you look at a reaction, if it's a redox reaction, what elements were, or what element was oxidized, what element was reduced? Like those are pretty typical questions. And you're going to be able to need to know what those terms are to be able to help identify them. And again, just to kind of try to put some other perspective on this, oxidation, we're always losing an electron, so it's always something, losing that one electron, leaving behind some kind of charged particle, or it's a differently charged particle than what you started with. Reduction being the exact opposite, so they really are kind of the same type of reaction, that's always happening here. And one of the things that's maybe kind of important to note with them is that as you look at kind of any given reaction, like you're never going to have just an oxidation or just a reduction. You pretty much can't have one without the other. Like you're not really going to have many oxidation reactions occurring unless there's also a reduction occurring that's kind of helping to drive why those electrons are being taken off or removed from something. So you pretty much always see them in tandem together. Now, the biggest part of this in terms of kind of things that we're probably going to need to learn for this section or for these reactions is the understanding how we determine oxidation states for elements. And so first off, comes real quick what an oxidation state is. It's kind of the perceived charge that an element has in the particular compound that takes into account its actual bonding environment, kind of what other elements it's bound to, how many bonds it has, how many lone pairs it has. Kind of takes all of that part into account to look at its kind of perceived charge. And the oxidation state or the oxidation number, it's really, really important because it's going to help us predict kind of what behavior certain compounds might have based on the oxidation states that certain elements have. So we know how to kind of predict the charges that ions for particular elements will have, right? Things like oxygen typically always being -2, things like calcium always typically being +2. the biggest thing here for oxidation numbers, you can kind of, once you assign oxidation states to things, when you get things that have oxidation states that don't match kind of their common ionic charge, it's likely those things are going to be pretty reactive. And so being able to look at and kind of determine oxidation states can be pretty useful for them helping figure out what things are likely to be fairly reactive or not reactive as a result. Now, in general, when we're talking about electrons and kind of what's going on, we kind of how we assign oxidation states is that when two atoms form a bond, we kind of assume that the more electronegative element, and what I mean by electronegative is simply that it's the element that has kind of the strongest pull on its electrons, particularly within actual bonds. Fluorine is going to be the one that's best at this, and it's kind of a trend. The kind of higher to the upper right of the corner of the periodic table you get, the closer to fluorine you get, the more electronegative things are. The farther down to the left you go, the less electronegative things are, with the exception of kind of one small, pocket in the kind of bottom of the D block, which we don't really worry too much about for general chemistry. But again, the part of the electronegativity that's important here is that the more electronegative element is going to pull electrons towards itself. So when we're assigning oxidation states, the more electronegative elements are typically going to have negative oxidation states. The less electronegative elements are typically going to have positive oxidation states in terms of how things are generally paired. Now, steps for determining oxidation states. Kind of good news, bad news. There are actual kind of set steps. It's very systematic, meaning if you just follow the steps, you should get to the correct answer every time. But you do have to kind of pay close attention to all of them as you're going through. And some of it looks probably more complicated than it is, at least starting out. Because some of it, really, once you kind of get used to it, you see a lot of patterns. It gets easier to kind of pick oxidation states of things. And you get used to what are the common oxidation states for certain elements, which then makes it easier also to pick out kind of when they're doing something unusual. Now, for our general order for assigning oxidation states to elements in an overall reaction, any element that's in its pure elemental form, so either like iron solid, carbon solid, or if it's diatomic, something like Cl2, it's still the elemental form for those elements. Those elements are always going to have an oxidation state of 0. And then in addition, this is also kind of an easy early step. Any atom that's actually an ion, as like a monatomic ion, its oxidation state will just match the charge. So for instance, if we have Fe2 plus as a cation, its oxidation state is +2. They just match. And so that part's not too bad. Where it gets a little weird is when we get to the bottom here, and then where it says the sum of all oxidation states of all the elements in a compound or a polyatomic ion must equal the total overall charge. So what does that mean? Well, it basically means if you have a neutral compound, all of your oxidation states have to add up to 0. Well, the way we go about assigning oxidation states then is we actually do have kind of a priority or almost kind of like a hierarchy system in terms of which elements have preference for their preferred oxidation state. And the list as far as kind of what that hierarchy is kind of is as follows. Group 1 and 2 metals are at the top of the list. They're always going to be +1 and +2. There will not be any exceptions to this. If you have a calcium compound, calcium will be +2. If you have a potassium compound, potassium is going to be +1. You're never going to see them really do anything different. The other one that I listed here is like, point B, but really this is probably on the same level. Fluorine is going to have an oxidation state of -1. We're not going to see anything in general chemistry that's ever going to make it be anything different. Now, the next one might seem a little out of order, and that's that hydrogen is going to be kind of third on this list, and hydrogen is typically going to be +1 unless it's paired with something above it, for instance, group 1 and 2 metals. Now, there are other instances where hydrogen might not be +1. We're only going to really worry about kind of the normal, kind of relatively straightforward examples for general chemistry. So hydrogen pretty much going to be +1 unless you put it with a group 1 or 2 metal for things we see in this class. After hydrogen, we get oxygen, which wants to be -2 for kind of the same reason its ion is always -2. And then thankfully, after oxygen, we go back to kind of just instead of individual elements, it's actually just columns on the periodic table. So after oxygen, we actually get all the rest of the halogens, like chlorine on down, they're going to be -1. After the halogens, we have the chalcogens, which is everything under oxygen, if you're not familiar with that term. So group 16 or 6A, all of those are going to be -2. Then we have the pnictogens, which is 5A, right? So like nitrogen, phosphorus, etc., going on down, typically -3 for their charge. And eventually, we're kind of continuing down this list. And when we stop is when we get to one element left. Because the last element, we're not going to follow this list anymore. The last element, since it's going to have the lowest priority for its oxidation state, is just going to take whatever charge is needed to balance the total charge for whatever a compound or polyatomic ion is. So, examples. I think this is the easiest way to kind of see the application of these things. So first we're going to determine the oxidation state of all the elements in the following compounds. So Cl2, pretty straightforward. Chlorine bound to itself. Those electrons are shared pretty evenly. There's no reason to have any charges. Anything bound to itself, to its pure elemental form, oxidation state is just 0. So that one's hopefully not too bad. If we have something like CO2, it's a pretty common compound, common example. If we're looking at assigning oxidation states, based on the hierarchy on the previous slide, oxygen is higher than carbon on that list. So as a result, each oxygen is going to get its preferred -2 charge. And then to balance the whole charge, since carbon's the only other element left, carbon must be +4 to balance the two -2 charges overall. And if we have something like sulfate, kind of following the same idea as what we did for CO2, we have 4 oxygens. Oxygen again is the higher priority, so all of them are -2. That's 4 -2 charges, but we have an overall -2. So if I have 4 -2 charges, that's a total of -8 from the oxygens. The only way I can get to -2 for the total charge is if sulfur has an oxidation state of +6. And so that's kind of how we're going through and looking at these and kind of trying to balance oxidation states in compounds. But don't get in the habit of oxygen always being the first element for priority, because then we do see examples like this one, where we have H2O2. If I'm assigning these oxidation states, and the hydrogen here in this case actually is the higher priority. And so that hydrogen is actually going to have a +1 oxidation state, meaning that if I have 2 hydrogens that are +1, if I have 2 oxygens, each oxygen is actually only -1 instead of -2. And so a good rule of thumb, if you ever hear a compound that has peroxide in its name, usually oxygen is in a -1 oxidation state in those particular compounds. It's kind of something to kind of just look out for. They don't pop up a ton in general chemistry, but you do see them more in organic as well. All right, so just a few more examples. Again, if you want to, one of the things I might suggest, especially if you're watching this as just at home, pause the video now, kind of assign these oxidation states on your own, and then unpause the video and kind of go through and see if your answers match what I'm going to go through. But for the first one, here we have hydrogen phosphate, HPO3 2-. Hydrogen phosphite. That is phosphite with the 3 oxygens. Phosphate is 4. So if I'm going to assign oxidation states, I'm just going to follow the hierarchy. Hydrogen's first priority. So hydrogen goes first. I'm going to assign it a +1 charge. Next, between phosphorus and oxygen would be oxygen. So each oxygen is -2. But now if I'm going to look at my totals, I have 3 -2 oxygens, 1 + 1 hydrogen. If I add up all those charges, that's -5. Well, if the whole thing has a -2 charge, that means phosphorus must have a +3 oxidation state. And this is a way to differentiate also between phosphites and phosphates, and really a lot of ites and ates. When you look at kind of the polyatomic formulas and the oxidation states, ates will also have a higher oxidation state than ites. That's why they have kind of the extra oxygen group if you're kind of trying to think about what's going on. And so it's just another kind of thing that can maybe help with some of that process while you're thinking about it. If we look at the next example, we have perchlorate, right? ClO4-. So assigning oxidation states, highest priority is oxygen. So oxygen will be -2, but I have 4 of them, right? So 4 -2 oxygen is going to give us a total of -8. If the whole thing's only -1, that means chlorine must actually be +7, which is part of the reason why perchlorate is so reactive. It wants to react to other things. It's why its salts are actually potentially even explosive and sensitive to touch and shock sensitive. So perchlorate, not expected to be super stable because that chlorine has such a weird oxidation state from what it would normally prefer. All right, if we look at N2O5, going through the same kind of motions, oxygen is going to be the highest priority, prefers to be -2. We have 5 of them, so it's -10. That means each nitrogen is going to be -5 to balance that total charge. Right, 2 plus 5, +5 oxidation state on nitrogen. 2 + 5 oxidation states on nitrogen will cancel the -10 charge from those 5 oxides. And then the last one, we have COCl2. Oxygen still has the first priority. It'll get to be -2. Next priority will be chlorine. They're each going to be -1. That means the total charge that carbon has to take in this case to balance everything must be +4. And so again, those are kind of the quick general steps in terms of applying that hierarchy that I had up a few slides ago to be able to help us figure out kind of oxidation states for things. Now, a couple other pieces here, and this a little bit of this will be just kind of identification and also a little bit on terminology. So when we talk about redox reactions, remember we are looking for electrons being transferred in the reaction. And again, if you're trying to pick out, like, for precipitation reactions, they're pretty easy to see because you have two aqueous reactants and a solid product. Acid-base neutralizations are pretty easy to see because you have an acid and a base reacting. Redox reactions are a little bit harder to identify at first, but one of the easy things I think to look for is whenever you have an element in its pure elemental form in the reaction, it's probably a redox reaction because that compound's probably not in its elemental form on the other side of the reaction when things are done. So for instance, here we see tin metal going to SnO2. Tin's oxidation state had to change. It has to be a redox reaction because of that. Now, in terms of identifying what's oxidized and reduced while looking at a reaction, I just mentioned here tin starts, this is tin metal, which means my oxidation state is 0. If I look at SnO2, 2 oxygens get priority, it's a total of -4. Tin is going to be +4 to balance all of that charge. So terminology, what we would say is that tin, the element tin, Sn, was oxidized from 0 to +4. And then if we want to identify, and then to figure out what's reduced, we go through kind of the same process. Look at the oxidation states of all the other elements. And when we do that, for nitric acid, hydrogen will be +1, each oxygen is -2. If there's 3 oxygens, it's -6, +1 from this means that nitrogen must be +5 to balance all the charge. So nitrogen starts out +5. On the product side, NO2, nitrogen, just like in SnO2, nitrogen is now +4 for an oxidation state. So its oxidation state went actually down, which means it gained the electron in this process. So the tin is being oxidized, the nitrogen as an element is what's being reduced. And then in terms of kind of the next piece of things, you'll also sometimes hear terminology like oxidizing agent or reducing agent, things of that nature, which we're going to look at next. But we need to be able to pick out what's oxidized and reduced first before we can kind of look at those other pieces. Now, one last thing I'll note before going to the next slide. If we see, in particular, I'm going to highlight here, the nitrogen went from +5 to +4, so it only gained 1 electron. Tin lost 4. Oops, sorry. But if we're looking here, there was 4 nitric acid, there's 4 nitrogens undergoing this change from +5 to +4. So there are 4 electrons total being gained for the 4 being lost by the 10. And we should always kind of see, hopefully, that balance when we're looking at our balanced reactions. Now, those terms I mentioned just a second ago, oxidizing agent and reducing agent, they can seem like when you actually see like what they represent, they can almost sound a little bit strange in terms of what how we figure them out. But an oxidizing agent is something that oxidizes something else. And the only way you can actually help oxidize something else is if you yourself actually get reduced. And so typically what we're going to see is the oxidizing agent is going to be the compound that contains the element being reduced. And even more specific, it's not even just the compound, it's actually the reactant specifically containing the element that's getting reduced that's going to be what we call our oxidizing agent. And then the other side of that, kind of the same idea, reducing agent is simply going to be the starting compound or starting reactant in particular that's going to contain the element getting oxidized. Because the reducing agent, in order to help reduce something else, it's going to contain what's getting oxidized and it's going to lose the electrons to help produce something else. So terminology and notation wise, we usually talk about certain elements or atoms being oxidized or reduced. But then we talk about in terms of like oxidizing and reducing agents, we're not talking about the individual element or atom anymore. We're talking about the full compound that's actually getting oxidized or reduced. All right, so identifying our oxidizing and reducing agents, just kind of some really quick examples. So this first one, if we're looking at it here, we have lithium 0 going to Li2O. Well, lithium in a compound is going to be +1. Oxygen is going to be the -2 it wants to be here. And here we have oxygen as a pure elemental gas. So oxidation state for lithium goes from 0. Over here, it would be +1. Oxidation state of oxygen goes from 0 to -2. And we have 2 lithiums that underwent that change, which is why our total electrons are balanced, right? We're going to have 2 lithiums that each lose an electron, and then we have our 1 oxygen that's going to gain those 2 electrons to be able to have a balanced reaction. If we look at our second example, we have Cl2 plus NaBr going to Br2 and 2 NaCl. So again, here we have chlorine. If we are assigning oxidation states here at 0, here it's -1, so chlorine is definitely getting reduced. Sodium is +1 to start, it's +1 at the end, so it doesn't actually change. And the bromide is going from -1 to 0. So the bromine must be getting reduced here, while the chlorine is going to get oxidized. Is kind of the way we refer to that in terms of the elements. But then our oxidizing and reducing agents, if the chlorine gas Cl2 is what's going to, if the element chlorine, excuse me, is what's getting reduced, that means Cl2 as a starting reagent is actually going to be the oxidizing agent, right? Because it's going to help oxidize something else by reducing that Cl2. Likewise, if we look at the bromine, bromine starts -1 and goes to 0, so bromine is actually getting oxidized in the process, which then makes the NABR the reducing agent in the reactions, the full compound that we always put in for that name. All right, now, a couple last bits before I wrap up for redox reactions, and we'll leave kind of some additional oxidation state assignments and also something with balancing redox reactions for the actual lecture, as I think that's easier to talk about in lecture than it is for me to just describe in a video. And then if I have to, I can always put up more examples in a video in the future. But combustion reactions, I've already mentioned, they're one of the most common types of redox reactions that we've already seen this semester, right? In those, oxygen gas is an oxidizing agent for that overall reaction. Another common example is actually just metals. If you have metals, they typically react with acids. Those are acid-base reactions that give off hydrogen gas. So your pure element doesn't even have to be a reactant, although a lot of times it is in these metal reactions. You can also be making a pure element as a product, and this means another sign that it's probably a redox reaction. I will note here, if you're looking in textbooks, there are sometimes things with activity series. We are not going to bother memorizing the activity series. It's just not that useful for us to memorize. There are many other things that we've seen in this chapter, like solubility rules are more important than the activity series to the things that we're doing. The activity series is something that will make a lot more sense if we go all the way to 1212 first, and then talk about electrochemistry and something called standard reduction potentials. That's what the activity series is actually related to in a lot of ways. All right, so last little bit here to kind of leave off right now is going to be identifying reaction types. So here, what I have is basically just some different reactions, and we want to identify what type of reaction they are out of the main 3 ones that we've talked about from this chapter, either precipitation, acid-base, or redox. Right. So if I look at, and if you want, you can pause and kind of come back and try your own, and then come back and look at the answers here in a moment. But for the first one, if we're looking at it, probably the biggest thing to recognize right away is we have a pure element on the reactant side. We actually have 2 of them, carbon and chlorine, as pure elements. They're not pure elements on the product side, so this should be a redox reaction. They're going to have to change oxidation states for that change to happen. For our second reaction, if we're looking at this, we have mercury nitrate and potassium bromide. And we have 2 aqueous reactants, and then again a solid product, which is going to be then our precipitate, because this is a precipitation reaction. Now, the third one down here is actually an interesting one, and I say that because there's really 2 possible answers you could put here. Right? First, you see aqueous plus aqueous makes a solid, so technically you could count it as a precipitation reaction, although realistically what it's probably more likely to be called is probably an acid-base reaction. Because you do have sulfuric acid plus barium hydroxide, making the BaSO4 and 2 water molecules. Now, last one, if we look at that bottom reaction, sorry, one more example, I almost skipped it. For the last one, we have C3H8 plus 5O2, making 3 carbon dioxide and 4 waters. There's no aqueous phase pieces here, but if we look at this reaction a little bit, hopefully we recognize 2 things. One, we do have pure elemental oxygen on the reactant side. 2, this is a combustion reaction that we just said a minute ago is always a redox reaction specifically. So in terms of the big picture reaction types, it is a redox reaction. If we wanted to be more specific, it is a combustion reaction that we're looking at there. Right. But I think this is a good introduction into kind of our oxidation states and kind of the starting things here for redox chemistry. We'll probably have a little bit more with balancing redox reactions that we'll see in the actual lecture part of the class that I'll talk about. And you'll see it kind of probably on the end of this PowerPoint, but I'm not going to put it in this video. I think it'll just be easier to kind of cover those examples in class and go through them together where people can ask questions a little more effectively, because that part is a little bit maybe more awkward than some of this early kind of more definition-based stuff for this section.